All right, let's get into it. Today, we're taking a journey deep, deep inside the Earth to uncover the fiery origins of the very ground we walk on. We're going to explore the incredible story of magma. I mean, really think about it. We see all this beautiful stone around us, right? In buildings, in our homes, but you probably don't stop and think about the unbelievably violent, superheated journey that rock took just to end up there. Just look at this. This is granite. And all those little interlocking crystals, the different colors and sizes, they tell a really dramatic story of creation. It's a story that starts with molten rock. So let's dive in. So here's our roadmap. We're going to start at the very beginning, the birthplace of these rocks. Then we'll follow the magma to a critical fork in the road. We'll explore the two different worlds it can create, one below, one above. And finally, we'll learn how to read the secret stories written in the rocks themselves. Okay, so our story kicks off tens of kilometers beneath our feet, in a world of just unimaginable pressure and heat, a place where solid rock literally melts. This is the birthplace of magma. So what exactly is magma? Well, it's not just simple liquid rock. It's way more complex. Think of it like a three-part slurry. You've got the molten liquid itself, sure, but you also have solid crystals that have already started to form, and then a bunch of super hot dissolved gases, mostly water and carbon dioxide, all swirled together. Now, here's a key point. Not all magma is the same. The one ingredient that changes everything is silica. See, magma that's high in silica, we call it felsic, is super thick and sticky, kind of like cold honey. On the other hand, magma that's low in silica, or mafic, is much hotter and way runnier. Think more like ketchup. And this difference, it's going to be absolutely crucial to our story. So as this molten rock starts to rise up through the crust, it gets to this critical moment, a fork in the road that is going to determine its ultimate fate and exactly what kind of rock it's going to become. And this image right here illustrates that choice perfectly. Does the magma run out of steam and just stall out deep underground where it cools slowly in a massive chamber called a pluton? Or does it find a way to the top and erupt from a volcano? This single decision, right here, changes everything. Okay, so this is the big takeaway. If magma cools inside the Earth, the rocks are called intrusive or plutonic. The cooling is incredibly slow, which gives large crystals time to grow. But if it erupts and cools outside on the surface, we call it lava at that point, the rocks are extrusive or volcanic. The cooling is super fast, so the crystals stay tiny. Let's follow that first path, the slow one. This is the journey of magma that never actually sees the light of day. Welcome to the world of plutonic rocks. I want you to just imagine a giant chamber of magma, completely insulated by kilometers of solid rock. It can take thousands, maybe even millions of years for it to finally cool down. This gives the atoms inside that melt all the time in the world to find each other and arrange themselves into these large, beautiful, interlocking crystal structures. And here you go. These are the results. On the left, you've got granite, which formed from that thick, high silica felsic magma. And on the right, that's gabbro, from the runnier, low silica mafic stuff. So what do they have in common? Look close. You can easily see the individual mineral grains with your naked eye, right? That coarse, grainy texture, that's the dead giveaway for slow, intrusive cooling. All right, let's switch gears and head down the other path, the fast and furious world of extrusive rocks, where magma bursts onto the surface in a volcanic eruption. So when that superheated magma, now it's called lava, hits the cool air or water on the surface, it's a massive thermal shock. It solidifies in just minutes or hours. The atoms are basically flash frozen right where they are, with zero time to organize into big crystals. And the result is a rock with a really, really fine-grained texture. Now check out this rock. This is rhyolite. And what's amazing is that it has the exact same chemical composition as the granite we just saw. It's made from the same high silica stuff. But because it cooled so fast on the surface, it looks completely different. You can't see any individual minerals. It's basically granite's volcanic twin. But that's not the only thing that happens during an eruption. Remember those dissolved gases we talked about? Well, as the lava hits the low pressure of the surface, those gases bubble out, just like when you pop open a can of soda. And what happens next is pretty incredible. So the lava cools down so fast that it literally freezes those gas bubbles in place. It creates a rock that's full of little holes. These holes are called vesicles. You're basically looking at the fossilized ghosts of ancient volcanic gas bubbles. But nature doesn't really like empty space. So over millions of years, groundwater that's rich with dissolved minerals seeps through the rock. It finds these empty little bubble holes and starts to deposit its minerals, layer by layer, slowly filling them in. And this is the spectacular result. It's called an amygdala. What used to be just an empty gas bubble has now become this beautiful, crystalline cavity. It's like finding a tiny hidden jewel box inside an ordinary volcanic rock. So we have slow cooling with big crystals and fast cooling with tiny crystals. Seems pretty simple, right? Well, geology loves to break the rules. Sometimes a single rock can tell two different stories at the exact same time. Take a close look at this one. What do you see? There are clearly big, dark crystals just sitting in a background matrix that's super fine-grained. It's a puzzle, isn't it? It's like it cooled both slowly and quickly. So how is that even possible? The answer is a two-stage cooling history. This magma started cooling really slowly deep underground, and that's when these large crystals, we call them phenocrysts, had time to grow. But then, before everything could turn solid, the whole chamber erupted, carrying these finished crystals along for the ride. The rest of the liquid then cooled super fast on the surface, forming that fine-grained background around them. This rock literally lived two lives. So you see, when you look at an igneous rock, you're not just looking at a collection of minerals. You're reading a story written in the language of texture. Big crystals tell you about a long, slow journey deep underground. Tiny crystals tell a tale of a fast, violent eruption. And a mix of the two, well, that tells an epic story of both worlds. So next time you see a granite countertop, a stone building, or even just a random pebble on the ground, take a closer look and ask yourself, what fiery story is this rock trying to tell me? Thanks for joining me on this one.